So this is a set you have to show the measure of this is smaller equal to 1 over c times integral over u. So what we observe is the following, and that is really all it takes. I can take absolute value of u and multiply it by the indicator function of b. Now, if I'm an x and I'm hit by this function, then two things can happen. Either the x belongs to b, then this is 1, and the x belongs to b, that this is greater than or equal to c. In that case, I have this is bigger than c. If x is outside of b, this is 0, and hence this is also 0. So this inequality holds for all x. So for all x in b, it holds because the limit is bigger than c, and for all x outside of b, it holds because those are 0. Also, this function here is between 0 and 1. So this is equal to absolute value of 2. So we have this very useful inequality. That means that the integral over u in u, because integral is monotone, is greater equal to integral over c times indicator function b in u. And this is by definition, take c outside, we get c measure of c times mu of b. And then we have found this greater equal to this is precisely the inequality we have. You just divide by c. There. Okay. So then we come to theorem 10.9. Which says the following. Suppose that we have, again, a measure space. And we have an integrable function. Then the following holds. If I take and integrate the absolute value of this function, and if I arrive at the value of 0, this happens if and only if u is equal to 0, mu almost everywhere. So in other words, mu is equal to 0, mu almost everywhere means that for all practical purposes, mu is equal to 0. For the practical purposes, I mean, as far as measure theory goes, we cannot distinguish these two functions from each other. The second statement says that for all n mu null sets, we have that the integral over n of u in u is equal to 0. So here we talk about integrating over subsets as defined here. So if you integrate any function over a null set, you get 0. So that's what the second statement says. So let us look at why this is the case. Prove it a little bit differently from the book. In particular, in one place I use a pretty dirty trick. I'll show you. Let's go first this way here. So we assume that this integral is 0, and then I want to show that u is 0 almost everywhere. So we put n to be the set of x, so that absolute value of u is strictly greater than 0. And note that, so enough to show, so the set of x where u of x is different from 0, this is precisely n. So if u is different from 0, that's the same thing as saying absolute value of u is greater than 0. So what we have to do is we have to show that n is a null set. In other words, we have to show that mu of n is 0. This is what we should show. And I really would like to use, this result here. Because this gives me a way of saying that mu of a certain set is less than something. The trouble is that here I have c is 0 basically. I want to use it, and then I get, this doesn't work for c equal to 0. I principally take infinity here. So I have to use this result, but I have to use it for positive c. And because of this, what we do is the following. I put an to be the set of x so that absolute value of u of x is greater equal to 1 over n. This is how we get around this. We consider this set for all n. All natural numbers n, we consider this set. So then what do we get? If we do this, then we get that for one thing that the sets here are increasing. They become bigger and bigger. And also, if we take the union of the sets, what is the union of these ANs? Take the union of them all, what do we get? We get precisely here. Because if I belong here, then we belong to one of them along the way. I could actually write this and make it more nicely as maybe it's nicer to write like this. It's the same thing. So being strictly bigger than 0 means that it belongs here eventually. And if it belongs here for any of the sets, certainly it also belongs here. So this is what we have. Also, by Markov inequality, we get that the mixture of an, what is that? That is less than c is equal to 1 over n. So 1 over c is equal to n. So here we have 1 over c, that is, this is n, and then the integral over absolute value of u. But this is 0. This integral is assumed to be 0. Hence, mu of an is 0 for all n. And then we conclude that mu of n, this is the limit of mu of an, and this is continuity of measures from below. And each of these is 0, so this is 0. So this proves this implication here. And it's the other direction where we can use a dirty trick, which is kind of useful. So for the other implication, still 1, but now this way. So here we have that u, so we have u is equal to 0, mu almost everywhere, and I want to show that the integral is 0. So then we put n to be the set of x, so that, again, as before, u is different from 0. Yeah, like this is fine. This is, by the way, the same as the set we had before. It's the same set as before. Then we know that the measure of n is 0. Because the assumption is that u is 0 almost everywhere. This is the same thing as saying this figure is measured 0. So this is what we know, and we want to prove that this holds. We know this and we want to prove this. here's what we do. We know the following. U is less equal to plus infinity times indicator function of n, absolute. So why is that the case? Well, if x belongs to n, then this is some number, and this is plus infinity, and any number is less than plus infinity. So for all x in n, this is good. And if x does not belong to n, well, if x is outside of n, then this is 0, and this is 0, that is also good. So in other words, this we have for all x. This is that. We have this equality here. And remember that we are allowing functions to attain the value plus infinity. This is part of the whole deal. And now we use it in a very practical manner. Okay, so this means that the integral, I want to show the integral of absolute value of u is 0. So now I can say the integral of absolute value of u in u. I'm using that the integral is monotone. I get this. And then I can take plus infinity outside. And this again is equal to plus infinity times mu of n. And this is plus infinity times 0 because n is at set of division 0. So we have plus infinity times 0, and what is that equal to? 0, yeah. And this is true in this course here. In measure theory, 0 times infinity is 0. If you look at other courses, it may not be true any longer, but in this course it's okay. So this is really a useful way of seeing this fact. Maybe I will skip the, well, maybe even I should recognize it. Put it. So let's also try to prove part 2. And let's see, let me just do it the right way. So, okay, yeah, so we note so what we have to note is the following: that absolute value of u times the indicator function of n, and here n is a null set. This is 0 mu almost everywhere. And this is because the set of x where this is non-zero is contained in n, and n is a null set. So this I absolutely believe in this fact. I'm interested in this fact further. Once we have this, we can then say take integral over n u du and take the absolute value. I want to show this is 0. And okay, so first of all, this is by definition equal to u times 1n in u. This is the definition of this integral. It's defined in this way. Then we use that inequality we saw last time, that we can take the absolute value and move it inside. And if I move it inside, I get absolute value of u times indicator n in u. But now this function is a positive function which is equal to 0 mu almost everywhere. And then by 1, I know that the integral is 0. Okay, then we come to so at the same time, not only do we prove useful statements here, we also, and this is something why I like these proofs, we see some of these fundamental properties of integrals being used. So it's useful to learn these proofs and see how they work. But this is also the reason I think why I'll just write some notes about it, since I do it a little bit differently than in the book. So we see how the theory is being used to prove these statements. Okay, we get a corollary 10.10. It says the following: suppose that u and v are measurable functions to be extended reals, and also suppose that they are equal mu almost everywhere. Then what can we say? Well, if u and v are positive, then they have the same intervals. So basically what we are saying here, there are two ways in which we can integrate them. We cannot integrate all these functions. We can integrate them if they're positive or if they are integral. So in both cases, it turns out that the integrals are the same. So in the positive case, they are the same, and in the L1 case, we can even say it even more, that if u is in L1, then the other one is also integrable automatically, and the two integrals are the same. So this is one of the things I said in the beginning, that two functions which are equal almost everywhere behave the same way as far as integrals go. So this is the claim, and you can even improve this in the next results in a rather nice way. Let me put the proof here. I guess I only proved part 2. We can't prove everything in this course. So first I want to show that the integral of v is that v is integrable. So we know that u is integrable. That is, we know that the integral of absolute value of u is finite. This is saying that u, the function u, is integrable. So now we want to show the same is true for v. Then we can use a triangle inequality to say that v is less than absolute value of u plus absolute value of v minus u. Moreover, v minus u is equal to 0 mu almost everywhere. And this is the same thing as saying that u and v are equal almost everywhere. It's just a reformulation. So hence we get that the integral absolute value of v in u less equal to the integral of u in mu plus integral v minus u in mu. This is finite, and this is 0 by the previous result. That was what was called 10.9. Part 1. So finite plus 0 is finite. So this shows that v is integrable. Let us see if I could have the same integral. And that is because of the following. I want to show that the integral of u in u is equal to the integral of v in u, assuming that they are equal almost everywhere. They have the same integral. So in other words, I want to show that this difference is 0. So I want to show this difference. Okay, but this is the same as using the linearity of the integral. I can say u minus v here. I keep it here. just saying what is written inside here is the same as this. Integral is linear. And then I use the famous inequality that we can take the absolute value inside the integral, and we get this. And now this function we know is this is equal to 0 mu almost everywhere. So this whole integral is 0. And this is by 10 I. And then we're done. So it's really some nice proofs. Let me see. Maybe I just state the next result and then we deserve a break. It's late. So I could go home. Yeah. And that is somehow the ultimate statement. I'll make it slightly less ultimate than the book. The book has an agenda, a hidden agenda, because he wants to do probability theory much later in the book. And we settle for this here, so I'll formulate in a slight discount version. And so I just say that the set G in the book will be A here. So ignore the set G basically, this is what I'm telling you to do. So we have X, A, comma mu is a measure space. And we have two functions. Let us say u and v are measurable functions on these technicals. And he calls it W, but let me just call it V. Then there are two different statements. Supposing first that they are integrable, both of them. Then u is equal to v mu almost everywhere, if and only if for all a in the sigma of a, the integral over a u du is equal to the integral over a v du. So if you have two integral functions, then they are equal almost everywhere, if and only if they have same integrals over all subsets. And this is really a very, very satisfying description of being almost equal almost everywhere. And somehow, if you were to look at it from a physicist point of view, if you think about a function, then you cannot, evaluating a function at a point is impossible. A point is just an infinitesimal point in the universe, and almost no physical point of view doesn't exist. What does exist might be sets, measurable sets, they exist. So this is something you can physically observe. So it's something you can say that these are all observations you can make of the function u, and similarly these are all the observations of the function v. And if they're identical, the two functions are equal almost everywhere. That's a way of saying this statement. This is a statement. Then there is another statement for positive functions. It's a little bit more subtle. You have to make it extra assumption. So maybe what I will do is I will leave it like this, and perhaps on Friday I will spend maybe just 10 minutes discussing this a little bit more. Then I will continue with the